question will be completely answered. So ask questions. It's up to you. It's for your benefit. So ask as many questions as you like. Yes.
Set D,
D number
number 4.
4.
Go over that.
Just a moment. Set D number 4. Number 4, right? Set D number 4. It is covered in textbook. Oh, I did not indicate the portion, so I will write the portion. It is page 113, theorem 6.7. So
Is number 5 in the text as well?
5 is also. I do not know why I didn't write down the. It's very strange that I did not write it. It is 6.8, theorem 6.8. Number 5 is 6.8. It is page 115. Set A number 3? Great. I, in fact, proved it before, so you can check the previous note, but I will prove it one more time. 10 to the power of 2p minus 10 to the power of p plus 1, where p is odd prime greater than 3. Then, as you can see, we can handle this number. So p is divided by 13, right? So the statement that we want to do is 13 divides this number. So 10 is equal to negative 3 with mod 13, right? So with mod 13, 10 is congruent to negative 3. 10 squared is congruent to negative 3 multiplied negative 3, 9. And then 10 cubed is congruent to, as you can see, negative 27, or negative 27 plus 13 times 2, right? 13 times 2, 13 is the modulus, so negative 1, right? Do you follow me or not? 10 to the power of 4, 10 to the power of 4 is multiplying these two numbers, negative 3 and negative 1. 3. 10 to the power of 5 is negative 9, or negative 9 is congruent to 4. 10 to the power of 6 is multiplying negative 1 twice, so 1. And as you can see, we can make a cycle, right? So it continues this way. Then, as you can see, and as you can see, 10 to the power of 6 times any number is congruent to 1, right? 6 times any number. Then we want to break up the number using 6, right? So division algorithm says any number n can be decomposed into 6 times k plus 0, 1, 2, 3, 4, 5. If you don't understand, ask me why we are doing this. Why are we doing these things? Because 10 to the power of 6 is congruent to 1. In other words, 6 and then something can be completely removed because it is congruent to 1. P is prime, so can P be this or not? Can P be this or not? Impossible or possible? Can P is prime? Is the right side prime? Is the right side prime? No way. So it's not. So P cannot be this. Can P be this? It's possible, right? 6k plus 1 is possible. Can P be this? 6k plus 3, 4, impossible, right? So P could be 6k plus 1 or minus 1. If you don't understand, ask me. In other words, P should be 6k plus 1 or 6k plus 5. There are only two ways. Other numbers are not prime. Why? Because if you have 6k, then 6 itself is not prime. If you have 6k plus 2, then you can extract 2. 2 times something, so it's not prime. And the same reasoning gives us the exclusion of these numbers. There are only two cases we need to consider. So let's consider one case. I think I considered this case when I solved the problem last time. So I will consider the other case this time. I might solve all the cases. I cannot remember it. You can return back to the note to find the portion. So assume that P is a prime having 6k plus 5 pattern, then 10 to the power of 2p minus 10 to the power of p plus 1 equals 10 to the power of 2 times p, 12k plus 5 times 10, and then 10 to the power of 6k plus 5 plus 1. And then by congruence, you can get rid of 10 to the power of 6. So 10 to the power of 4 here, and then 10 to the power of 5 here, and then 1 here. If you don't understand, ask me. Because 10 to the power of 6 is 1. 10 to the power of 6, or any multiple of 6 is equal to 1. 1 multiplied by anything is itself.
How did we get the 6k, the p was equal to 6k plus some number?
I use the division algorithm. If you have an integer, we can divide any integer. We can divide any integer by 6. Then if you divide n by 6, then there is quotient k, and the remainder, there are 6 possible remainders. If you divide n by 6, there are 6 possible remainders. And among these, 6k is not prime, 6k plus 2 is not prime, so only primes can occur only at these two cases. In other words, the power could be this or this. Other cases have non-prime powers.
Well, my question is, why 10 to the 6th power? Why not 10 to the 4th or something like that? How does that relate to the
So
prime?
6k is 1. Yes.
Can you go back up?
Yeah. So 10 to the power of 6 is 1, and then once it is 1, we can return back to 1 all the time and then continue.
In the book for that group, it just kind of jumps to the 6k plus 1, 6k plus 5. It doesn't go through the, it doesn't show it as, it just kind of makes you think that you need to know 6k plus 1 and 6k plus 5.
I
are the
see.
numbers. So it's harder to read in the book.
I see. I see. So as I mentioned before, 6k plus 2 or 6k are disqualified because they have non-prime powers, right? Non-prime, right? 6k cannot be prime. And now 10 to the power of 4, I calculated 10 to the power of 4 is 3, right? 10 to the power of 4. So it is congruent to 3 minus 4 plus 1, and then 0. It means 13 divides the right side. This is it. And then you can do the similar steps on the other case. So that means we solve the problem. Ask any questions that you want. You don't have to wait until someone else asks questions.
So since 6k plus 5 works, we don't have to go back and do 6k plus 1.
We should do both. We should do both.
On the test, you want us to show both?
Yes, right. But because other step is almost identical, I don't want to spend too much time. But if any of you want, then I will do. I don't have any obligation. I already made a problem set. So no matter what you ask, I don't know. It's your luck. It could. Someone might already ask a question that is questioned on the exam.
Answer number 1. Any questions?
Usually, proof questions.
Number, set A, number 5.
I will do it. So good. Oh, in fact, I should mention this thing on the exam. This is not exactly this one, but this type can be questioned with 2 digits. In other words, x is congruent to 2-digit number mod 2-digit number, and then x is congruent to 2-digit number mod 2-digit number, and then so it's possible. Why? Because if I ask just 1-digit number, someone may use all the numbers directly and then find the solution without knowing the technique. Then it's very difficult for me to give an appropriate score. But if I ask 2-digit, you may spend whole exam time to find the number from like a scratch. Almost impossible finding in class hour, in exam hours. It's impossible to find the solution by using 1 through like 1,000. It's almost impossible in class hours. So I ask 2-digit numbers like this. But in this case, I asked just this case. But if you want to change it, you can make up. Do you want me to solve exactly the same problem as this one, or do you want to make up? Because exam doesn't ask this same set. Never. Then you may pick any 2-digit number. So 1 digit at a time. So each person may just pick one number between 5 and then what?
3.
3 and then what?
2.
And then
7.
7. And then 1, 2, 3, 4, 5, 6, 7, 1. So if you want to change it, change it. First of all, the moduli should be relatively prime. It's not required to have primes on the right side, but they should be relatively prime. So check it. 27 and 34 has no common factor other than 1. And similarly, 71 and 34, 27 and 72, so none. So they are relatively prime. Then, once these are relatively prime, then we are done. How? X equals the product of these numbers, 27, 34, 71, all multiplied together is called n, right? Then n over the first number, first modulus, 27, right? And then multiply by the inverse of this number, mod 27, and then 53. So you need to multiply these type of 3 numbers, that's it, right? So on the exam, you may try to use this technique. Then even though you do not have enough time to get the conclusion, you may get some partial credit. In fact, significant partial credit. But assume that you are using your like scratching out technique or elimination technique. Then you may pick 1, and if 1 doesn't work, you pick 2, and then 2 doesn't work, 3, all the way up to 1,000 or 10,000. Even if you get the correct solution, you don't get full credit. So there are big differences between this theory, right? This is from theorem called Chinese remainder theorem, and ad hoc approach or just canceling out approach. Then the remaining thing is the calculation of individual numbers. But if you don't know what the next term is, then let's compose. What should come here? N over what? 34. And the same number, N over 34. Inverse should come here with mod what? 34. And then one number should come here? 12. And then N over what? 71. And then N over 71. Inverse. And then 71. And then 56. So by writing it, at least theoretically you completed. Then out of like 100%, by just writing this, you may get significant portion, like over 60% you may already obtain by just spending like 2 minutes, less than 2 minutes. But while someone made a huge chart from 1 through 1,000 and remove all the numbers, may not get any point, or may get just 1%. So the only thing remaining is the calculation of the inverse. First of all, we need to find n. N equals, so you need to know how to multiply. 27, 34, 27, 34, and then 71. So I will multiply. 27 multiplied by 34. Then 7 times 4 is, I will make the boundaries so that you are not confused. But if you are familiar with these things already, 28, right? If you multiply 7 and 3, 21. Multiply 2 and 6, 26. Multiply 2 and 4, 8. Then 8, and then multiplied here, 9, right? 9, 18 multiplied by 71. It's not very difficult, but I'm practicing it so that you can understand the structure behind it. Because these numbers are trivial, I will just write it 8, 1, 9, right? Now this number, 56, and this number. Then we can add these 8, and then 7, and then 12, and then 9, 21, and then 6, right? So n is found. N equals 6, 5, 1, 7, 8. Wow, it took like 2 minutes. So on the exam, because the calculator is not allowed, you need to know some technique like this, or whatever you can use. It doesn't matter. Anything you can use. Now, this divide by first modulus 27. 27 gives us like 2, and then 54 subtracted, then 11, then about 4 is too much. 4 is okay, right? 5 is too much, right? 4 is okay. Then it is like 37. Then it is like 108, then 4, right? So it is 2414. 2414. So unless you stop me, I will go to the next page. Very strange. Did we use all columns? Wow, we used all columns. Two 2414 inverse should be found, right? 2414 inverse with 27 should be found, right? So to find it, what should we do? 2414 divided by 27. Then 2414 divided by 27 gives us about 9 might work, right? Is 9 too much or not? If we subtract, then it is 5, 25, right? And then 27 and 9 might work this time, right? Then if we subtract, I'm not good at the multiplication table. $11, right? So 11 is the remainder. If you divide this number by 27, then the quotient is 9, and divide remainder is 11. To confirm that I didn't make any mistake, I will divide it by, so I will calculate mod 2414 by 27, then it should be 11. Right? 11 is correct. Any questions? 11 is correct. So as you can see, 11 is found. If you divide 27 by 11, then the quotient is 2 and remainder is 5. Do you see it? If you divide this, by the way, 89 should be recorded, 2 should be recorded, and then if you divide 11 by 5, then the remainder is 2, and the quotient is 2, remainder is 1. If you divide 5 by 1, then the quotient is 5, and the remainder is 0. This is it, right? This is the Euclidean algorithm that I mentioned before. And what should we do? We are calculating this. This times x plus this modulus y equals 1, right? We are solving this kind of equation, right? In other words, we want to track down possible solutions for these numbers. So I do not want to review the stuff that we studied for the exam 1. So all we need to do is writing down 1, 0, right? Do you know the meaning of 1, 0? I wrote down upstairs, right? Above, right? 1 times 2414 equals 2414. Do you see it or not? If you don't see it, I will re-explain. And then 0 means 0 times 2414, and then 27 times something. Then I can continue the same step. I can multiply this and subtract. I can multiply this and subtract, and I can multiply this and subtract. Then 5 is the answer. So let's write down 5 times mod 2414 multiplied by 5 mod 27. Then it should be 1, right? According to our calculation, it should be 1. So I have found the inverse. Something multiplied by x gives us 1. This number is called inverse. Inverse is 5. If you don't understand, ask me. It all came from the solution that if you don't understand, you may go to the second lecture, right? Second lecture to find the explanation of this. So take a look. I'm forming all the necessary terms So solution X is congruent to 2, 4, 1, 4. Multiply by 5, multiply by 50 something. Do you have the record? 53 plus other terms, right? Because these are tedious, I'm just writing it. And then mod n. N happen to be a big number, right? Mod n. I don't have n record, so mod n. But you should be careful. This multiplied by this is 1 with mod 27, right? With mod 27, this multiplied by this is 1, but with this is not, right? Do you see it? This is 1 mod 27, but with mod this one is not 1. This is the key. This is the key. So you can calculate the other terms similar way to find the solution, right? To find the solution. If you want all the steps, I can spend whole hours to do these things. But if you don't,
Is that sufficient for full credit, just to be able to say that?
full credit means up to the end. So it's like this. I will show you the breakup. So assume that you mention about Chinese remainder theorem or you use Chinese remainder theorem. I may give 60%, right? And then for appropriate, appropriate setup, like n over something, then I may give like 15%, right? And then for the calculation, I may give like 15%. And then for the correct solution, 10%. Then this could be the breakup of the points. In other words, you mentioned about Chinese remainder theorem and then the form. But, what I meant is the form that I wrote down, not just Chinese remainder. You cannot just say, problem is Chinese using Chinese remainder theorem. That does not mean 60%. So what I meant is, so it's a little bit awkward. So I wrote down something, right? That kind of term is called is 60%. And then other things are calculation of n over something, and then calculation, these steps. And then
You want us to get down to full credit, X is congruent to a single.
that one is the result. For instance, X is congruent to like 952. Then this gives you the full credit 100%. But if you cannot reach this, then you may stop at some appropriate point that you feel comfortable. But if you just mention, you can solve this problem by using Chinese remainder theorem, then I will worry about giving 1% or 0%, because it's nothing. So what? You know, sorry. You cannot just say, you can solve the problem by using the Chinese remainder. You cannot say that. But you should show what Chinese theorem says, right? What Chinese theorem says. That is the part that you can get huge credit. Not just, you can solve the problem. Then should I give 1% or 0%? I should worry about the choice of these two. But as I mentioned before, I can spend a whole hour solving this one. But if you want other things, ask me. Sorry, I should have. I should kill the. Any questions?
Set D, part 1, when you're talking about driving those things like the Euler's theorem, 137. What is it? Do you just want us to quote the theorem?
Just set D and the problem what?
Number 1, like Euler's theorem, page 137. Do you just want us to quote the theorem, or do you want something else? for an answer to the
I see. So when I said state, it means state. Just state the theorem. That's it. When I say prove, then you should prove. Oh, so there was a question. Assume that I ask you to prove this. Assume that I ask you to prove, for instance, this. This is not a good example. I have a better example. Then you can use anything up to this point. Up to previous theorem, not this theorem, or some theorem using this already. In other words, to prove it, you can use anything that you learn. But if some theorem was proved because of this, then it's not possible to use that kind of group to prove it. In other words, this theorem happened here. Then anything that we learned up to this point could be used, right? Anything. But sometimes there was further developed. There could be further development of the theorem, and there could be generalization of this theorem. You cannot use this to prove it. Why? Because this generalization came from this. So without proving it, how can you prove it? So it's impossible to come down, but it's possible to use anything up to this point, right? Up to this point. Just before the theorem is possible. Any fact that you know. But something that you cannot use is like advanced one. You know, prove Fermat theorem, then because of Euler's theorem, Fermat theorem is true. It's not possible, right? Euler's theorem is far more general than Fermat theorem. Do you know what I mean or not? In other words, assume that I asked you to prove Fermat theorem. Right? Assume that I asked you to prove this, then because by Euler's theorem, phi to the power is 1, right? By Euler's theorem, phi to the power of 1, and then phi to the power of p is p minus 1. So this is true. I don't accept this kind of proof. It's 0 point. Absolutely 0 point. Why? Because this is far general than the theorem. So you cannot use Euler's theorem to prove Fermat theorem. It's impossible. If you want to use it, prove it and then use it. That means proving the theorem. But anything before that is okay. Do you understand what I mean? So if I asked you to prove it, you would use something before Fermat or Euler's theorem, not Euler's theorem. So if you write it, you may think, I did pretty nice job on the second exam. No. When you receive the result, you will see 0 point. Why? Because I write down just one comment. Why? Right? Why? This is the key of the proof. But you use the key, then it's not acceptable. In other words, when you want to prove something, you need to use, in fact, in the previous exam, some people used some fact from algebra to prove the irrationality of, I think it was 2 raised to square root 2. So some student used some fact in algebra to prove it, but that algebra part already assumed that this is irrational. So it is not acceptable. I didn't give any point. The statement was correct. The statement was correct, but it was not a proof. Do you understand what I mean? So even if your statement is correct, you may get 0 point because of this. So whenever you ask to prove something, use anything before it, not after it, or the generalized form, but itself, or before, right? Something before it to prove itself, right? Same thing is like Wilson's theorem. Assume that I asked you to prove that 1 multiply up to p minus 1 is congruent to -1, then you cannot say that, oh, it is 1. You cannot use this thing to prove this, or you cannot use this line to prove. These are equivalent. In other words, by using this, you may prove of the above relation, and vice versa. But these are like a circular logic. We need to prove at least one line to prove the other. If you use the other line, then it is just a change of the statement. What you did is the change of the statement, not proof, not the proof. Do you understand what I mean? So do not change the statement. Changing the statement wastes your time and do not give you any point. So if I ask you to prove this kind of Wilson theorem, then you need to prove, oh, sorry, why did I say that? 2. Right? So if you are asked to prove Wilson's theorem, then you need to prove this kind of statement. And by this statement, you can get the conclusion. Or by proving it, you can get this conclusion. Either way is possible. But you cannot just say, oh, because of this is true, then I don't give any point. So when you are asked to prove it, always use that doesn't involve the statement or changing of the statement, right? Just changing of the statement is not the proof. Any more questions on proofs? Let me check how many are proofs. First one is prove. Second one is also prove. Third one is also prove. Fourth one is calculate. Fifth one is calculate. So 3 proofs and 2 calculations. And one definitely questioned problem is this. Prove that this is multiplicative. So this is questioned. As I mentioned before, by just reading through the note, you will get 20% of the second exam, right? 20%, 20 points by just studying this about 10 minutes, right? Or maybe 5 minutes if you read the note. Oh, no problem, no problem. I can spend 1 hour on this.
I actually don't know if I have very good notes on that.
So, show that phi of n is multiplicative, then if the GCD of Mn and then like any number is 1, then GCD of Mk is 1 and GCD of Nk is 1. You can use this fact to prove it. You don't have to prove this fact. You can use this. You can use this statement. I, in fact, proved these steps. Then afterwards, you line up the numbers 1 through Mn. 1, 2, 3, up to M. And then in between, R, right? R. And then M plus 1, M plus 2, and then M plus R, and then 2M, and then 2M plus R, all the way up to N minus 1 M plus R, and then Mn. And then you write it. And then you state that in this group, some number is qualified, some number is not qualified, right? For instance, this number is qualified, right? In this group. And the total number of numbers in this group is what? P of m, right? Total number of qualified numbers is P of m. Do you get it? So among these, some numbers are qualified. Let's say R is qualified. So these are qualified numbers satisfying the condition. Yes?
Does it say n plus?
N minus 1. This portion, right? N minus 1.
So it's sufficient to state that out of the top row, only phi sub n are qualified.
Right, phi sub n elements are qualified from 1 through n by the definition of phi sub n. You don't understand? Ask. Then, the next statement you can mention is, let's go to the next page. The next step that you can mention is, if P of M, P of R, right? I will use, if GCD of Rm is 1, then GCD of any m multiple, right? Any m multiple plus Rm is also 1. That means once top number is qualified with respect to m, then any number in the column is qualified with respect to m. Because of this, the whole column is qualified. With respect to m, right? We are checking the relatively prime numbers with respect to prime numbers to m, right? So we are finding relatively prime numbers to m. If you have a question up to this point, ask me. Then, in expression, this is the qualified column, and somewhere qualified column, and then qualified column, and so on, right? So these are qualified column, and some column has R, right? R, M plus R, 2M plus R. These are qualified columns, right? These are qualified columns that we can use with respect to M. So these are qualified columns. And total number of columns is what? Phi of M by the definition of phi. Any questions up to this point? Then next step is picking on specific columns such as this one, right? We can pick on this specific column. And then for this column, we show that R, M plus R, and then 2M plus R, and then N minus 1 M plus R is congruent to 1 through N, right? Not element-wise, but set-wise. How can you do it? That is the key. How can you show that these entries are, as a set, congruent to 1 through N? How can you do it? The idea is showing that if we pick two different values here, it will arrive at two different values, right? If we pick two different values, they will arrive at two different values, or we can reverse it. If we have the same statement described a little bit differently is, if we pick a specific number, say k, then it came from this and this somewhere, right? Then they cannot be different, right? This and this are in fact the same entry. So we can prove, in other words, there are 35 seats here, there are 35 students outside, then they can come and then take one position. The only exception is what? 2 students cannot be at one chair, right? Cannot be on one chair, right? So this is the key point. Do you understand what I mean or not? So what you want to do is this kind of thing. Pick specific entry such as I times M plus R, right? I pick some number in between I and then J M plus R happen to be same position, right? So we assume that they happen to be the same, right? Same means they happen to be congruent. So if this happens, then all I need to show is they are in fact equal. I and J are equal. In other words, one position means one student, not 2 students. That means they are spread all over 1 through n, right? This number is congruent to 1 through n. So in each column, this happens, then we can get rid of R, right? And we can divide by, we can use the cancellation law. What is the cancellation law? Cancellation law says I is congruent to J mod what? Mod what? N over what? GCD. GCD of M and N. What is the GCD of M and N? By the condition, GCD of M and N is what? 1. So 1. And then it is 1, right? So they are the same, right? I and J are the same. So because of this reason, this statement is true, right? This claim is true. And then how many entries are relatively prime to n among these things by the definition of the phi function? How many entries are relatively prime to n by the definition? Phi of n. So in each column we can find phi of n. So now I will write the summary of the proof. Phi of mn, when mn are relatively prime, is equal to the number of qualified columns, right? The number of qualified columns with respect to m, right? And then for each column, right? For each column, we pick the number of entries relatively prime to n, right? With respect to n, right? Entries. So this is the summary of the proof. Then, by the definition of the phi function, the number of qualified column is what? Phi of m. And the number of entries, 1 through n, is P of n. So this is the proof. So very short, right? So we have proved that phi is multiplicative. This is absolutely asked on the exam. Like this?
Yeah, and just down.
So take a look. Can you read it? This is problem number 3.
Did you actually go down to the bottom of that page?
In the book?
Oh, thank you.
As you can see, cancellation law is extremely important, right? In theory, in proof, in calculation, everywhere, right? Cancellation law. I mentioned this more than 30 times in class. Cancellation. When you cancel out common numbers like m, right? Then apply the cancellation law. Cancellation law use that m and then modulus, right? Such as n. Of course, this is in the book, and if you don't understand the statement that I mentioned, you can return to page number did I write the page number? I did not. Page number 133. Now you can ask more questions. Ask more questions. More questions.
Get the page numbers for set F.
Oh, I was a little surprised. I thought I wrote down the page number, so I will tell you. Set F, so I will tell you the page number. In fact, I will write the page number.
On which?
Set F. Set F. What was I thinking? I thought I wrote all the page numbers. So I will grab that part and then take a snapshot and then write the page number. That way you don't have to rewrite it. So I write the page number. This is, in fact, it is not very difficult to find the page number on your own, but it is time consuming. So I will write the page number. It is page 141, theorem 7.6, and this is page 144, theorem 7.8, and then this is page 151, corollary, and this is page and in fact, I proved this last time. Where is the... I think this is the problem. So it is page 153, corollary, and I wrote the problem. But if you need any explanation, ask me. I will solve any case or explain any case. By the way, the summary of the final chapter that we covered, assume that we have a number, then it may or may not have primitive root, right? Primitive root is, by definition, what? Primitive. Primitive root is the number satisfying this. 1 for any k between 1 and phi of n, right? Only possibility is by Euler's theorem, then this number, right? This kind of number A is called primitive, right? Primitive root. So primitive root of n is A, right? That A satisfy this kind of condition. It is not congruent one for any number between 1 and phi of n. The first time that it happens is when the power is phi of n. When it's prime, such as p, then phi of p is p minus 1, right? So a to the power of p minus 1 is congruent to 1. And it is called primitive. So we are not very interested in this kind of calculation. We are more interested in the number of numbers, number of primitive roots. Number of primitive roots is equal to what? Very easy, phi of n, if it exists. If it doesn't exist, how many? 0. If it exists, phi of n. If it doesn't exist, how many? 0. Then when does it exist? When n equals what? N equals 2, 4, odd prime power, 2 times odd prime power, then it exists and is the case like this. Otherwise, the number of primitive number equals 0. Done. So we are more interested in this kind of theoretical stuff. Find the number of primitive numbers. Then, it is a bonus question, right? If it's asked. It's very easy. Phi of n. Very easy. But you may pick any number, then I will find the number of primitive numbers. So any number is okay. What number do you want? Pick a number. 27. So, excuse me? 100. That's too much. Let's use 27. Then phi of n equals phi of 27, or 3 to the power of 3, right? 3 to the power of 3. Then 3 to the power of 3 minus 3 to the power of 2. 27 minus 9, 18. So phi of n equals phi of 18, and then phi of 18 equals 18 multiplied by 1 minus 1/2, 1 minus 1/3, because 18 is equal to 2 times 3 squared, right? So 18 written here, and then 1 minus 1 over this prime factor, 1 over this prime factor, right? 1 over 1 minus, right? 1 minus 1 over this prime factor. Then because of this, we can calculate the number 18, 1/2, 2/3, and then total 6. So there are 6 primitive roots for the number that you chose, or I modified, 27. But if you want other number, I will do it. If you want more numbers, then I will do it. What number do you want? I will do 127. I feel guilty. So let's check whether it's prime or not. Yes, it is prime. So let's factor 127. So if I factor it, it's itself, because it's prime. When it's prime, phi of something is very trivial. Phi of this is very trivial. It is 127 minus 1, or 126. Very trivial, right? So phi of 127 equals phi of 126 equals 126 multiplied by 1 minus 1/2, right? 126 equals 2 times 53. Do you see it? 120, 63. 126 is 2 times 63. 63 is 3 times 3 is 9 times 7, right? 3 squared times 7. So because of this reason, what should be attached here? 1 minus 1 over what? And then 1 minus 1 over what? 7. So I'm reviewing the calculation of phi function. At least 20 times in class I calculated phi function by hand. By computer I did more than 1,000 times, because I run it in the loop. I ran those things in the loop. So let's finish this calculation. 126, I will write it upstairs. I will write it here. 126 multiplied by 1/2 multiplied by 2/3 multiplied by 6/7. Then I can cancel out these numbers, and I can cancel out this number, and then I can cancel out this number. It is 1 and then 8. So 36 is the result. There are 36 primitive roots of 127 that you chose, right? Any number, pick any number. So I reviewed many things, many cases. But if you still have a question, ask me. Any case is okay. As I mentioned before, I don't gain or lose anything. You may gain a lot if you are lucky, because you may hit the jackpot. In other words, in fact, someone already asked the question that was here, right? Right here, someone asked. Lisa?
So can you do it?
Once you spot it, I will.
Do I need more question? I think it's Am I right?
So I cannot say anything. The only thing is picking. For instance, if you are lucky enough, you may ask all 5 questions, like set A, number 5, set B, number 2, and then those could be already questions. Yeah, complete answer. I will not hide anything.
We can still ask questions Monday.
The same style, and then Monday, you may ask any questions or anything. This is complete for you. If you don't have anything to ask, you don't have to be here. Why should you come here? Of course, you may use the arc. You can use the archive. It's all recorded. Then instead of keeping you in the room, you may do anything you want, and you may approach and ask questions. And someone may feel embarrassed to ask questions. That might be important, but you may approach and ask questions. Whose pen is this? If you didn't grab your result. But this is a big problem. In fact, it happened after the final exam. Someone didn't write down the name on the final exam. Then how can I know who the person is, right? Someone may just skip or didn't come, or how can I know? It's very bad, right? On your way out, you can confirm that the problem was really questioned. I cannot show you other pages, but on your way out, you can confirm that the problem was questioned.
So is that only 5 questions?
5 questions.
That's the multiplicative.
Yes, right.
Number 3, right?
Number 3. So this is the actual exam that you will see on the day of the exam, right?
Is it exactly for
Excuse me?
Is it exactly for
No, those are just samples, right? As I mentioned before, I changed the numbers or I changed the style or selection. Not very much, but I changed a little bit. This one is exactly the one. Because this, once you know this, you know a lot, right? This is the major reason why I'm giving away the point. So like today, next time is for you. If you don't have anything to question me, then don't even come. You can just email me. But if you have many things to question me, then you can come and then.
And are you gonna, after this test, do the same thing for our final, for our practice finals?
Very similar type final question, right? See,
No, I don't need to see that.
I want to see it.
Okay.
That's it?
I had surgery on my shoulder.